Well, here are the Maxwell relations. So this is a little out of order from the book. Okay, so this is near the end of this chapter. However, I want to show you a really nifty trick, how we can come up with all of these equations without having to memorize anything besides a simple mnemonic. And also, as we move forward in this class, we're going to see how having a key or a cipher or a mnemonic to quickly recall these relationships, how useful that's going to be. So the Maxwell relations are the second derivatives of our four thermodynamic potentials with respect to their natural variables. Okay, those four thermodynamic potentials are the internal energy, okay, internal energy U, all right, and what we note here, what we see, which we didn't know before, what we're learning now, the natural variables that we're seeing of internal energy are V and S, volume and entropy. Unexpected. That would be unexpected. Okay. The other one we've talked about, enthalpy, H. Okay. And from this, we should interpret that enthalpy's natural variables are pressure and entropy. We kind of already saw that before, where we noted that constant volume heat capacity is related to internal energy and constant pressure heat capacity is related to enthalpy. But as it turns out, they're also related, each of them, to entropy. Okay, so what is this A? This A is called the Helmholtz energy. It's really the Helmholtz free energy. Okay, A. And we can see A is a function of T and V. Sometimes this is also called the maximum work function. Okay. And also G, hopefully you recognize G. This is the Gibbs free energy. G, which is a function of T and P. Okay. Also, this is often referred to as the maximum work function. Okay. So we haven't talked about Helmholtz or Gibbs yet, but I'm going to be introducing those very shortly. We've spent a fair amount of time already talking about internal energy and enthalpy, and I'm kind of diverting from the flow of the lecture to talk about these Maxwell relations and what I'm going to introduce next as the Thermosquare, so that we can organize ourselves and keep track of all of these partial derivatives. Because if you're staring at this, like thinking like, oh my God, this is a mess. It is a mess. And I'm going to show you a really clever trick of how you can always recall these relationships. So this is called the Thermosquare. This is a little trick that I learned in graduate school. I did not learn this as an undergrad. I would have been like really grateful to have learned this as an undergrad because I had flashcards for all of these things and it was a giant pain in the butt. My grad instructor showed us how to do the Thermosquare. Hallelujah. Okay, so the first thing you have to do is come up with a mnemonic to remember this. Okay, so what you do have to memorize is this: VAT, UG, SHP, arrow pointing from S to T, and arrow pointing from P to V. So you have to remember this, okay? So my thermo instructor from grad school taught us to remember it by verified analysis of verified analysis and, not that that matters, but verified analysis and thermodynamic understanding gives solutions to hard problems. Okay. VAT, UG, SHP. Now, so this is what my grad professor gave us. I will tell you right now, none of my friends in grad school, none of us actually used this one. We came up with our own, and it was kind of crude and had some dirty words in it. I'm not going to tell you what it is. You have to come up with one yourself. So I said that to the class last year, and the best thing they came up with was VAT, UG, SHIP. And honestly, now that's the only thing that I can remember is VAT, UG, SHIP. So however you want to remember it, VAT, UG, SHIP, verified analysis of thermodynamic understanding gives solutions to hard problems, or you come up with your own. Any way you want to do it, memorize this, commit this to memory, and you will be able to recall all of these relationships. Here is how we do it, okay? There is a process. I'm going to walk you through it. I've got 2 thermosquares on this slide. I've got 2 more thermosquares on this slide. I'm going to do all 4 of those potentials and show you how we get it, okay? So let's start with H, okay? Suppose we want to know about H. We identify it, okay? There it is. The first thing I'm going to do, I'm going to say the partial of H. And now what I'm going to do is draw a little horseshoe. Okay, this is how this works. You draw a little horseshoe like so with H or a U, whatever you want to call this thing, a trough, whatever. Do it like this with H at the bottom and in the middle. Okay? We recognize H is sandwiched between the S and the P. Okay? So now I can say this is a second derivative. So the second derivative of H with respect to S and P. H is sandwiched between S and P. Equals. Okay? Now what we recognize is because S and P are our natural variables, we are going to have derivatives with constant S and derivatives with constant P. So we can set that up. Okay? And then now I'm going to go over to the S. I could go with the P. It doesn't matter which one I start. But I wrote S right here first, so let's go to S. I'm going to travel up this arrow. Okay? Follow along the arrow. I end at T, or I get to T. I'm going to write dt. Okay? I come all the way down my little like trough thing that I drew, right? T, I go down to P and say partial of P, and that's all at constant S. So now I go over to my constant P. I travel with the arrow. I get V, partial of V by partial of S at constant P. Okay, so let's remember that. The Maxwell relation for H says dt by dP at constant S equals dV by ds at constant P. Let's see how we did. Aha! dt by dP at constant S equals dV by ds at constant P. Sweet. Okay, let's do U. Okay, so now this thing is flipped on its side. So we're still going to make this little horseshoe thing, but we're going to rotate the horseshoe. Okay, we're going to rotate it. And now I can write, okay, U. So I know a second derivative in U, and it's sandwiched between the V and the S. Partial of V, partial of S equals. And I know that now I'm going to have derivatives at constant, let's do constant S, and derivatives at constant V. Okay? And so now, same thing. Let's travel to the S, travel up the arrow, and I get to T, dt, and then I'm going to travel up the arrow and work my way back to U. Okay? So dt by dV. Okay? I'm trying not to cheat, but it's just so hard. Like, I got the equations right in front of me. The whole idea of this thing is that you do it without looking at any of the equations, right? So that's how you can practice this, by not looking at the equations. Don't cheat like I am. Okay. So let's see if I can do the other one without cheating. But now look, when I go to V, look what happened. The arrow didn't change, and the arrow is supposed to stay fixed like this each time. Okay? So now when I'm at V, constant V here, I'm traveling against the arrow. And because I'm traveling against the arrow, I'm going to put a negative sign. Okay, that's what that arrow sign is all about. All right? And so now I go to V, I travel against the arrow, and I get that that's partial of P, work my way back to U by partial of S at constant V. Let's see how we did for U. Look at this. Here we go. There's that negative sign. Partial of P by partial of S at constant V. And yeah, partial of P by constant S at constant V. Okay, great. Okay, let's keep going. Let's do the other potentials. Okay? So let's do Helmholtz, A. Okay? So we draw the little horseshoe, but now my horseshoe is completely flipped upside down. Okay? I can see that A is sandwiched between T and V. So I'm going to write partial of V, partial of T. Okay, beautiful. And I know I'm going to have derivatives at constant V and derivatives at constant T. So let's go to the V. And now you can see I have to work my way against the arrow. So that's a negative sign. And that's going to be partial of P by partial of T at constant V. And then now when I go to T, I'm also going against the arrow. So that's also a negative. And now that goes to partial of S by partial of V at constant T. And yes, I got all that right. And so I know you're thinking negative, why not cancel the negatives? Well, you can. And so what you would say is negative Helmholtz with respect to volume and temperature equals the positive of these quantities, right? So positive partial P, T, and V, and partial S, partial V at constant T. So you could also write the relationship like that as well. Okay? And then finally for Gibbs, free energy, G, we're going to draw our little horseshoe, rotate it around for G. Okay? I can see G is sandwiched between T and P. Okay? P. Let's do that again so it looks better. Partial of T, partial of P, P and T. Okay, so now I know I'm going to have derivatives at constant T and derivatives at constant P. And let's go to our T. Okay, so look, T, I'm going against the arrow. So it's a negative sign. I end up at S, partial of S, by partial of P, constant T, equals. And then now I go to the P, travel up the arrow to V. That's going to be the partial of V by the partial of T, all at constant P. And did I do that one right? Yup, I got it. Okay, folks, so this is incredibly useful. I know it's kind of out of context right now, but in the coming lecture, which will probably be a little bit longer than the others, because I'm going to connect all of this, we will see how incredibly useful it is to connect these variables, or to connect these potentials. And to also be able to see, it's not straightforward yet, what are the natural variables of these things? I think we've kind of seen that constant volume corresponds with internal energy and constant pressure corresponds with enthalpy, but it's not intuitive, these other connections. Okay, so Thermo Square, Fat UG ship, verified analysis of thermodynamic understanding gives solutions to hard problems, or however you want to memorize it, remember it, and practice this. Practice getting these potentials. Okay, I'm going to move forward, and we'll see how this gets connected. Okay.